Good morning. We are starting lecture number 26 today. Again, I'm Professor Ananta Agarwal at the Department of Electrical and Computer Engineering at the Ohio State University, and my colleague Dr. Arash Salmi is here, and he has helped me prepare these slides. With that, let's talk today about the short circuit capability of silicon carbide power MOSFETs. So, we have been talking about the planar power MOSFET structure, which we call D-MOSFET, and we will talk about the short circuit capability of these MOSFETs. So, let's talk about the basic structure of the silicon carbide D-MOSFET shown here on the left. And just to remind you, this dimension here is channel length. We have gate oxide, polysilicon gate, and plus source. This region here we call the JFET region, and here is the drift layer. And when we turn on the gate, there is a MOS channel of electrons. We call that inversion layer. It's formed here, and then the current flows from N plus source through the channel down the JFET and down the drift region, where it spreads and gets collected by the substrate. All right. So, now in this simulation, and this is only showing the half the cell, the other half cell is mirror image on the right hand side, and then this cell is repeated millions of times in a given MOSFET, as you learn in the layout and processing section that Dr. Arash Salmi had taught. Now, in this simulation, we are going to change the channel length from 0.3 micron to 2 micron and look at the on resistance of this cell at gate voltage of 20 volts. So, we have applied 20 volts on the gate. We have assumed that the channel electron mobility is 10 centimeter square per volt second, and we are changing the channel length from 0.3 micron to 2 microns and plotting the on characteristics in the first quadrant, drain current versus drain voltage. And you can see as we increase the channel length, the current reduces at a given drain voltage. That means the on resistance is going up as expected, because the MOS channel forms a big part of the overall on resistance. So, if you remember, the on resistance was the sum of the channel resistance, the JFET resistance, the drift layer spreading resistance, substrate resistance, and the contact resistance here. And for these 1200 volt structures, the channel resistance is 70% of the total resistance. So, that is the biggest component, and obviously that resistance goes up as we increase the channel length. So, increasing the channel length is a bad idea, and that is why most of the vendors are using 0.5 micron channel length. And the reason is, of course, that the electron mobility is only 10 centimeter square per volt second. In silicon, that is like 400. So, we have a big disadvantage in silicon carbide devices, but we make up for that by using short channel length. Now, when we use short channel length, we have another problem that comes up, and that's the saturation current is very high. So here we have taken the same structure as in the previous slide, and we have plotted the drain current versus drain voltage at a gate voltage of 20 volts for different channel lengths. So in the previous slide we were looking at the on state for low drain voltages, but here we want to go and see what happens at 1200 volts. So you can see that for short channel devices, the current is very high at 1200 volt or 1000 volt in this case. Let's take 1000 volt. This current is extremely high, whereas in the on state we will be operating somewhere around 1.5 volts. So the current is 6 microamp per half cell. But for the same half cell, the current at 1000 volts of drain bias is 50 microamp. So we went from 6 microamp for usable current in the on state to almost 50 microamps at 1000 volts of drain. Now that's pretty high, almost 8 times, and this is happening because we have a short channel length. When we go to longer channel length, you can see we can reduce this current at 1000 volts. But why is this current important at 1000 volt? And that is because of the short circuit rating of the device. So in power electronic circuits, there will be times when the device may accidentally get short circuited, meaning it will operate at the full voltage and full current. So you can imagine if you are sitting at 1000 volts and carrying the full current, there is a lot of heat dissipation, and that heat dissipation will destroy the device. The temperature will rise so high that the aluminum overlayer will melt, the passivation will peel off, and basically the device becomes a big black chunk of carbon. So the application standards are that this device should last for 10 microseconds without getting destroyed if it were to be short circuited. Now that means we have to keep the heat dissipation low when we are short circuited, and that means we have to reduce this current from this point to this point as low as possible, so that the total heat we are generating under short circuit condition, which is 1000 volts times this current, is small, which will then extend our short circuit time. How long can device last under short circuit is important. 10 microseconds is the goal. Alright, so that's why increasing the channel length is a good idea, because you can reduce the saturation current at high voltages, but it is not a good idea because then the on resistance in the on state really goes up, current reduces, and then the device size has to be increased and the cost goes up. And all this is because our inversion layer mobility is very low compared to silicon. So supposing we still want to use half a micron channel length, but we don't want very high saturation current at high drain voltages. What can we do to make this happen? Now in this slide we show what happens when we go to 0.3 micron channel length. So remember 0.5 micron is here, the blue line, and then 2 micron is down here in the noise. But look at 0.3 micron, the current becomes almost 1 milliamp. So 6 microamp on state current to 1 milliamp under short circuit is a huge range, and this device will certainly be destroyed within a microsecond or less. This current is so high. Even half micron, this current is very high. So, what is going on? So, if we look at the electric field at this point, which we call point A, right here where my laser marker is, and we look at the electric field at that point when the drain voltage is high, like 1200 volts, full blocking voltage. What happens to the electric field at this point as a function of channel length? And that electric field we have plotted here. At 2 microns, that electric field is almost 2 megavolt per centimeter. But as we reduce the channel length, that electric field goes up to 4.5 megavolt per centimeter. So, when you have a very high field here, which is coming essentially because of the high drain voltage, the channel length, effective channel length is shortened because of that electric field there, and it is called the drain induced barrier lowering effect or the short channel effect, and therefore the high saturation current takes place. So, then the idea is by increasing the channel length we can reduce that field at point A. So, the question is what else can we do to reduce the electric field at point A. So, again that electric field we have plotted here as a function of channel length, and you can see it kind of saturates for long channel at 2 megavolt per centimeter, but for short channels it exceeds 4 megavolt per centimeter. And we already decided we don't want to increase our channel length because the device cost goes up. So, we have to find something else. So, here is an idea. This is not our idea, this has been published by other people. We have given you one reference down here, and this is called the shielded P plus structure. What we have done is taken the same structure, but all we have done is put this P plus layer at the bottom of the P well, which is highly doped 1E19 per centimeter cube, and now this thickness we can play with, right. Nothing else has changed, everything else is the same. So, the thickness here is 0.2 micron, and here is the conventional structure with 0.5 micron channel length at 20 volts. You can see the current goes up very rapidly with drain voltage, but if we use the shielded structure with D equals to 0.2 micron and channel length of still 0.5 micron, we have not changed the channel length. You can see you can suppress the saturation current by factor of 2 right here. That means your heat dissipation is reduced by factor of 2. That means your short circuit time has increased by factor of 2. Compare that current now with conventional channel length of 1 micron without the P plus shielding, and you can see we can get to the same point by half a micron channel length in a shielded MOSFET. So, all we have to do is keep your channel length at half a micron and put this P plus shielding here. So, that's that's good, and what that does, it pushes the electric field out here into the JFET region at a given drain voltage, and that helps deplete this area in such a way that the field at point A, where my laser marker is reduced by just having a P plus. So it's very simple, the cost is minimal, no design changes, no mask changes, just add an extra implant stuff or step or P plus, and it's a very simple change. And you can double your short circuit time by just doing that. So here we have done the same simulation where we have varied the D from 0.2 to 0.4 micron, and you can see there is no major effect. 0.2 micron is good enough. We like 0.2 micron instead of 0.4. Why is that? Because 0.4 means the cost goes up. We have to do longer implantation cycle, ion implantation cycles. So the shorter we can make it, the cheaper it's going to be to implement it. So 0.2 micron is good enough. So what is going on? Again, we look at the electric field at point A, and we already have plotted the electric field as a function of channel length in the traditional structure here. And here at 0.5 micron, you can see the shielded MOSFET structure has reduced the electric field from 3 megavolt per centimeter to more like 2.5 megavolt per centimeter. And that's the same thing shown here. The electric field at point A has been reduced by about 0.5 megavolt per centimeter. So that helps reduce the short circuit current and therefore increase the short circuit time. And if you look at the on resistance at low drain voltages for conventional structure versus shielded MOSFET structure, basically both for half a micron channel length, basically there is no effect on the on resistance because we will be operating somewhere at 1.5 to 2 volts, so right here somewhere. So here there is no effect. So basically without having to affect the on resistance of the device, we can improve the short circuit time at high drain voltages in this structure, as opposed to the case of higher channel length where the on resistance is affected. So the method of increasing the channel length is not preferred, but there is a simple fix. We can keep a short channel length and just put the shielded P plus region. So what are the other ideas for reducing short circuit current? One standard idea is put a resistor in the source of the MOSFET. This is called this resistor here. It's a temperature sensitive resistor, so when it gets hot the value goes up. So under the on state there is current flowing, the drain current flows through this resistor, and under the on state this resistance is small, so the voltage drop across this resistance is small and nothing really changes too much. But at high currents this resistance start heating up and the value of this resistance goes up. As a result, the drop across this resistance goes up, which subtracts from the gate source voltage right here. So the effectively we have reduced the gate source voltage being applied to the MOSFET because of the voltage drop across the resistance, external resistance in the source. So basically this is a negative feedback effect. It's used in bipolar devices for current sharing. It's a very common idea. But the price we are paying, of course, is that for low currents under the on state, this resistance adds to the on resistance of the MOSFET. So, it's not free, your on resistance goes up a little bit. Professor Baliga and his group came up with a nice idea recently. Here's the reference, they presented this. Instead of putting the resistor there, they replaced that resistor with the depletion mode silicon MOSFET in series with the source. So, it's a large silicon MOSFET, it's depletion mode, meaning it is on, and they connect the drain to the gate. Then it just becomes a 2-terminal device. You can look at the reference. So, basically it is like putting this resistance, but if you look at the MOSFET characteristics of a depletion mode MOSFET with drain connected to the gate, the resistance, the IV characteristics look like this. They just saturate, which means at low currents and low voltages, it's a linear resistance, but at high voltages, that resistance becomes very high because the current saturates. So, that is an ideal thing. You want high resistance when you are in short circuit and low resistance when you are in on state. So, these are two things that a circuit designer can do by putting a resistor or a depletion mode silicon MOSFET externally to the device. Inside the device, I think the designers we can look at this reducing the JFET gap. I know we have been using a JFET gap of 2 micron. If we reduce it to 1.5 micron or even 1 micron, we can drastically reduce the electric field at point A that I had mentioned, and that will be much more effective solution without having to put an extra component externally. So, this is where the research is going. We have shown, a number of people have shown that this is a good method of doing that, but when you reduce the JFET, then the JFET resistance will go up, which means you have to increase the n-type doping in the JFET region. So, that optimization has to be done. Finally, a good solution may also be use some other metal as a overlayer. Right now we use aluminum, which has a melting point of 660 degrees C. So, when the device temperature under short circuit goes up to 660, aluminum starts to melt, it diffuses inside the transistor, shorts everything out, and eventually it blows up. But if we have a metal like molybdenum, we call it moly, with a melting point of 2600 degrees C as opposed to aluminum, then it will last much longer and will not melt, and your short circuit time which would be much longer. So, these are simple solutions one can employ. The last two within the device and the first two external to the device. We can also try to put this resistance in the source inside the device. Mitsubishi has done that, number of people are doing that. Then the designer does not have to put an external source resistance, but again the limitation is the same, your on resistance goes up, whereas in the P plus shielded region, P plus shielded MOSFET, the on resistance does not go up. Reducing the JFET gap and increasing the JFET doping will not affect the on resistance, but it will reduce the short circuit current and so on. So, with that, let me stop here, and next time we are going to come back and talk about super junction transistors. So thank you very much, and we'll see you next time.